Anyway, so I think there were a few people that had similar questions. So I'm gonna be the dumb guy that try to understand the concept. So we have our real data,
yes.
We make the association indices,
yes.
that table, and we do also all the permutation.
Yes.
Okay? And we look whether the CV or the standard deviation, which is a measure of the dispersion on the real data,
exactly.
is higher than the permutated data. Is that correct? So that means basically you have much more dispersion, so most likely there is either a preference or avoidance, because the dispersion can go on one side or the other.
Perfect.
Good. Everyone? Good. Okay. Now, the main question was here. Now, if we have a short-term preferred, and we want to test for preferred or avoidance companionship, okay, within sampling periods, so within blocks, only for permit group within periods, yeah? This would, I would read it, lower, if we find a lower mean in the real data compared to the permutated data,
yes.
that means that my real data has got less than what would randomly occur,
yes.
which means is closer to 0 than to 1, so I could expect more an avoidance companionship. How a lower mean means a preferred, unless it's a lower or higher.
I do know what I mean, and I can't quite remember.
Okay.
That's what I was trying to look at it.
Okay, so we can look at
but
it.
That's, yeah, that's...
Am I understanding correct?
Yes, that's exactly what I mean. So, where is the low mean of the observed association index will indicate either preferred or avoided companionships within sampling periods when compared to the permutations.
Yes.
But exactly why?
Why?
I
Okay.
can't quite remember. I can't get my head around it right now, but I'll get back to this.
So it's lower than what I expected. Okay, yeah. And last thing here, if we look at gregariousness among individuals, so
yes.
some individuals where they stay in larger group or smaller group,
yes.
again, is a matter of variability within your data.
Yes.
Of typical. What is typical group size?
So
is it a mean?
I did look that up.
Yeah, it's
a big formula.
Is it?
yeah.
So forget about it's one of these things in biology is accepted, basically.
But it's the yeah, it's a big formula, but the concept.
I looked it up. Do you just want the quick definition?
Yeah.
It's the arithmetic mean or crowding measures averaged over the individuals in a group. So, and crowding means the number of individuals in a group. So it's the mean.
So it's the mean of the
mean of the number of individuals in a group averaged over the number of individuals.
So it's a mean.
Yeah.
No.
Yeah.
No.
No, is that a mean? Is that a mean?
No.
That's it. Okay.
Let me see. In another way of defining is typical group size sizes are the group sizes experienced by the individuals. That's actually
So the most frequent ones. So the
yes.
group number that occurs the most within a population.
yeah. So that individual is usually with
So
four others.
It's a mode. If it's a most frequent, is a mode.
I'm not sure how it's calculated in the permutation tests.
But anyway, whoever wants to read more can read that chapter.
So Ralph, I just like put it on
But
the desktop and then
I think it's normally lower than the mean group size if I
then
remember.
you should be
Or
asking.
lower than mean group size. Okay, yeah. But again, it's not too much that is
Just
yeah,
just to answer
yeah.
that. So when there's two ways of testing for gregariousness. One of them is the permutation test for gregariousness. So you're gonna test the standard deviation
Yeah.
or the CV of the
Yeah.
mean number of associates of each individual in a sampling period. So, so
Okay.
it's pretty much how many individuals that guy is with. Could
All
be
the
three,
time.
could be, see, if over time is just 3, 4, 3,
Yeah.
4, 3, 4, that's one thing. And now, if sometimes it's 17, 2, there's much variation. So the
That
typical,
means-
yeah, the typical group size is the number of associates that guy is
So
usually
there is
seeing.
whether there is a variation in gregariousness,
Yes.
basically,
Yeah.
and that's basically what it is
So
about.
if the groups is more or less same size, or there's
Compared to the permutated data.
yes. So we're testing for individuals. So is there
Yes.
any individual that is usually with 17 individuals and
Yeah.
other is usually with just 2? So these guys are more gregarious than
Then
this
it-
one.
okay,
Testing
perfect.
for-
So the point 2 is the only
So now it's just the mean.
the mean the
Yeah.
y mean lower mean refers to both preferred and avoided.
Oh,
Mean permeate.
so,
Sorry,
oh, I think I have one at Lattice.
Yeah, but yeah, I don't know what I forgot about that. So I'll look it up for sure. Let me. So I'll just show. We're a little bit behind the schedule, but that's fine. I'll just show you how to do this on SockProg now, and tomorrow in the new model class lecture for the network analysis, we're gonna do essentially the same thing, but then in R step by step, and then you can see how it works. But here in SockProg would be just defining some parameters and then clicking run, it will do all the permutation for us. Tomorrow we're gonna see step by step. So to run this, for those of you who didn't skip the class, you can go straight from entering your data, defining sampling periods, association, and then when we get at this in this window here, this is where we're going to run our test. So here we define the type of test we want, if it's permuting everything, permuting with things sample, or permuting the association matrix. Here we define the number of flips. So if you put 1 here, from each new matrix, it will just flip 1 submatrix. So usually you put 1,000, but if you have a smaller samples, smaller data, we might want to reduce this. And here's the number of permutations. So usually at least 1,000. And for now we can put just 100, so otherwise it will just take hours to run if you have a lot of data. But if you have a lot of data, you might want to put 20,000 and let it run overnight. Sometimes it takes a lot of time. And if you want to test for those pairs of individuals, like here with the whales, and it will give us for each pair, if we reject the hypothesis, it will spit it out which are the pairs of individuals that are consistently seen together, or the preferred or the avoided. Anyway, if you want to stand that, we just have to set up here the alpha value, so usually 0.05 for this, and then we let it run. Now, let's do it. Here. Then I'll show you how to get to that window.
Don't worry.
So, everyone, for those that's good. If you can open the MATLAB or SockProg. Just see here. There we go. So see if you can start inputting these data here, the scene group N, and also the supplement, and then do all of the basic steps we did yesterday. My lab doesn't like the projector or anything.
Is it?
Yeah, it just freezes all the time. So we'll define I'll define the association as the group variable. Not going to use any restriction. And for now, we'll just put sampling period as a day. Is that everybody more or less here? We go to associations. Okay. Getting a lot of error message. It's too big. Can't see.
Is there a message related to the projector?
Uh,
Are there messages related to the projector?
if it's messing up with the projector? is
No.
that-
It's not a soft problem.
Is it?
Errors are a soft problem, is that what you're doing?
Yeah. No, it's just
Oh,
if I use the normal view here, then you cannot. It's just too small. I don't know if people can see that.
That's fine.
So is everybody more or less here? Yes. So here we have the three. Well, I hope you can see. And if you click there, you're gonna see the three options for permutations. You're gonna choose just to start now. Permute all groups. So is that unrestricted permutation? We're just gonna flip the whole thing. Okay. So do it. Permute all groups, and you can leave maybe 100 flips per permutation here. So the number of the trials per permutation is just the number of submatrix they will choose each step. So if you want to do the classic one, it's just one, or the recommended is 1,000, but depends on your data. In here, over here is the number of permutations. So usually you want to do at least 1,000 and up to 20,000. It actually depends on your data. It's good to start small and then see the p-values and then run more and see if the p-values vary way too much, then you have to increase the number of permutations. There's usually 20,000 is a good number. You're gonna have a pretty solid result, but it might take an entire night to run. So for now, let's just do 100 to go real quick, and then we'll test it. And this is the, yeah, and this is the output. Not very exciting. So if you can see there, so we have the output here, our sampling period, if there's any restriction, the type of association you're using, the association index, the type of permutation, here permuting all groups, so permuting everything, number of individuals, number of flips per permutation, and number of permutations. And here's the table. Now this new version of SOCPROG is much more organized. It's easy to understand what's going on. So we have all those statistics, mean, CV, SD, proportion, all of this, and then you choose the one is the best for you or according to your question, right? So it gives you the real value, the mean of the mean value of the random matrix, so the 100 matrix we created over here, the proportion, which is the same as your p-value over here. So if you were testing for long-term relationships, we could either look at the standard deviation or the coefficient of variation of the association index. In this case, the real one is CV, for example, is 0.99, and the mean random one is 0.53. So there's a big difference here, and the p-value for that is 0.01. So only in one random matrix, so we got a higher value for CV than the real one. Does that make sense? Really? Good?
Say again, sorry?
Okay, so we have, let me see. We have,
No, just
all right. We have, here is the number of random matrices we have, 100.
yeah.
Here's the number of random
Okay.
matrices that we have that is higher than the original one. The real value is here. So for CV, we have the real CV of our matrix is 0.999. And the mean value for all the random matrices is 0.53, okay? So out of 100 random matrices, just one of these 100 matrices had a CV that is higher than the observed one. So our p-value is 1%. So if you have a distribution of CVs here, so this is random CV of association index. So whatever that is, let's say it's this shape. So we have 100 CVs here, 1, 2, 3, 4, 5. And then the observed CV is more or less over here. So that's the observed one. So just one random matrix was higher than the observed value. And 99 of them were lower than this. So this is a good indication that our observed association matrix, there's more variability in the association index than expected by chance. So in our observed association matrix, we have very low values and very high values. And when you shuffle that around, it tends to be more or less the same. So you got, does that make sense?
So that's when you mean that you're looking for a high CV because it's so high that only one is higher than that.
That's right. And same for the, so remember for long-term preferred or avoided relationships, we can also look at the standard deviation, which is another metric. Well, it's pretty much So the standard deviation, the CV is actually standard deviation divided by mean, right? It's just a standardized version of the variation. So here, the real one, we got 0.9, and the mean of 100 random matrices is 0.12. So all of the random matrices had a lower SG than the real one. And this is why our p-value is 0 here. So here has some suggestion. SG is a good test for preferred associations, and CV is the recommended test. So if you want to look at those, you can just ignore mean, ignore all of that. Doesn't matter. And if you want to test for the gregariousness, it gives you the standard deviation of the group, typical group size.
Yeah.
So the standard deviation is pretty high, 0.82, and the mean random one is 0.43. So that means in your real data, you have more variability in group sizes than expected by chance. So yes, there is evidence that some individuals are seeing larger groups and others are seeing smaller groups. Now, the idea is the same. If you want to look for short-term relationships, then you look at the mean value. And the mean value here is smaller than the random one. And now I will give you a few hours to figure out why is that. But yeah, according to following the recipe, that also means you also have short-term preferred associations. So this is the output for the new version of the sock product. If you're working with the previous one, the output is a little bit messier. I don't know, is that someone using this one? It's the same, but it's just more confusing. But the results are the same. It's just not organized in a nice table. And that confused a lot of people for a lot of time, including myself. Then we talked about how, can you please make a nice thing? Organize that. So the way it used to be is, it gives you first all these stats for the real associations, then all the stats for the random associations, and then all the p-values. Right. So, for example, here the mean association index is this. And in the case of preferred associations, you're going to look at the CV, right? So you look at this is the real CV, this is the random CV, and here's the confusing part. This is the p-value for the CV. It's just the way it's presented is confusing, but it's the same thing in the other one. Same here, you just put in a table one, the other, and the p-value. But it's the same thing.
Are we working with the same data here? Because the values are different. No? It's not the same data?
No,
it's different data. Okay.
Yeah, it's a different example.
Oh, okay.
This is just a screenshot.
Just the output. Okay.
And so, and this is another thing that was confusing.
Why 0.029?
It's 1 minus this, because now it gives you, this is the one-sided, one-tailed test, so you're just looking to one side. Anyway, the way it was so complicated. Larger p indicates large real value compared to the random value. Anyway, so if you're using the new one, forget about this. If you're using the older one, it just it's a little bit more complicated to understand. And okay, let's see what happened here. Good. So go back to this guy. So I didn't. If you want to test, with this test, we rejected the null hypothesis. So there are some preferred and some avoided relationships. Now, if you want to see which pairs are preferred and which ones are avoided, we can add here. I cannot even read. but it can add here alpha value, so 0.05 will give us the pairwise results. So let's go ahead and do that.
Can you redo the screen resolution? What you did before was reading very nice.
This one?
No, that's it.
Or
And the other one? The other resolution? No, that's one. There was another one. The other. Oh, no, it's this one. It was before. On system preferences, on top. Yeah. Then we go system preferences. I goes back there. It was reading fine, and you did something.
Yeah, I mean,
Okay.
it's a little bit better. So here again, if you put the alpha value for the dyad, the pairs of individuals, it will give you here a list individual in this case. So we have 34 significant dyads. So we have individual 4 and 1. So the index is 0.82 and the p-value for that is 0.98 and so on. So it would just be the same thing here, but for each pair of individuals. So you can look. I think the expected number of significant pairs is 9.5, and you found 34. You have a question? So over here in the so here you have to put your alpha value here. Yes. It might take a little while.
Is it 0.05 or is it 0.5?
You said?
Yeah, it sounds better. I think it's getting hot.
No, it has to receive because some every now and then it becomes stupid.
And then at the very end, it will give you also the pairwise results for gregariousness. So the typical group size is
0.05? 0.05?
no, that's the significant level.
Sorry.
So for this guy, for example, individual 17, his typical group size is 4.5 individuals. This one is 3.5, and they are significantly found in larger groups, and that's the typical group size. You have just 4 individuals. That's why we rejected that hypothesis. So it's just breaking down which pairs of individuals are making you reject the hypothesis over here. Is that all good? Yeah, a little bit late, I guess. Let's see. Good. So let me just give you some recommendations. So later there's some exercises we can try the other algorithms, but the idea is the same. I just run for the permuting all groups. But then remember, if you want a more powerful or more robust test, then you select the appropriate sampling period and then just run within the sampling periods to remove the demographic effect. And so it takes a lot of time, so it's good to start with maybe 1,000 iterations, 1,000 null matrices, and you do 100 flips per time, then you check the p-values, and usually you're gonna have a lot of variation at the beginning, and the more randomizations you do, up to 20,000, you will tend to be more robust, more stable results. So you start with low just to see how it works, and then once you figure out the best parameters for your test, then you go ahead with 20,000, go to sleep, and then check in a week after more or less. And what else?
What do you mean, once you figure out the best parameter for your test?
It depends, well, it depends the data you're using. For example, sampling period, you want to see if you want to get if it's too short, too long. So you want to run this a bunch of times until you get more or less consistent results. Same for for the number of matrices. Like if you run 100 times, you're gonna have, you compare your results with just 100 new matrices, right? So if your data is very well structured, with 100 models, you're gonna see the pattern right away. Then if you run at 20,000, it won't change that much. So if it starts changing too much, you better increase more, so you just get a better, a more stable result. So we just increase to 5,000, and until you get until you keep checking your p-values and everything is more or less the same, that means you got it right. And if you want to test for the pairs of individuals, you might want to run 20,000 just to make sure. Good. All right, we're a little bit late, but I'll still go through this. So just there's two other concepts that I would like to introduce here: social differentiation and social representation, because those will give us idea of the power of this analysis. So remember that testing these null hypotheses is almost like a first step from all of the other patterns we want to see. First of all, is everything happening just by chance or not? If it's everything happening by chance, so there might be not much point in go much further than this. So we're gonna test this, but let's see if this test is actually powerful enough to give us a good idea. So first, we need a lot of data, unless it's the social structure is very obvious. You have like these pretty clear social units. You have these very solitary individuals, these very gregarious ones. If there's a lot of variation, then with the few data, you're gonna pick up those patterns. If everything is more or less homogeneous, then you need more data to extract that. So the more the merrier. Just to give an example, for an association index of 0.5, 50% of the times, two individuals are seen together. And here, X is the number of sampling intervals this pair of individuals were associated. So, let me see. If you have in your data set just 4 times, these two guys, A and B, were seen 4 times, then, let me see. That means lots of data is shared. Okay. I forgot this part. So if you have just seen these guys 4 times, your standard error and coefficient of variation will be pretty high. So that means the chances are when you compare it with the random data, this will be shown as a significant pattern. But the more you increase, now you're seeing 16 times, this drops to 9. If you're seeing 100 times, you drop to 0.004. So then the more you have, and if this thing tends to decrease, so the variation tends to decrease, and in this case, if you can still reject your null hypothesis, then you have a lot of power to say, okay, there is a pattern here. So with few data, it's often you're gonna have like this pattern when there actually don't exist. So see how much variation we get with few observations, and then when we increase these observations, we get a much more precise estimate of our association index. So this means we need a lot of data to have an accurate association index. But truly, seeing two guys 100 times is pretty rare. And often we work with these low, so just keep that in mind. So one way of testing these, the variation in the data is what we call social differentiation, the so-called ASP from now on. What it means is the coefficient of variation of the true association index, of the actual time that individuals spend together compared to the association index, which is an estimate of the proportion of time individuals seen together. It's almost the same, but it's not. So one is the actual proportion of time individuals will associate. You gotta estimate that. And the other one is the coefficient of variation of the association index. Okay, there it is. So what it means actually with the social differentiation will inform us how heterogeneous the social system is. So if S, the coefficient of variation of the true time they spend together is more or less around 3, all the associations are more or less the same. If it's around 0.5, they're all right, well differentiated. If it's super high, then it's very well differentiated. And we estimate that using bootstraps. In 2 days from now, I'm going to show you how to do that by hand. And the way we estimate this is using either Poisson or likelihood methods. So we are estimating the actual time and comparing it with the association index. And the other concept is social representation. So it's the correlation between these two things, the association index and the coefficient of variation of the true association, the true time they spend together. These terms are super similar. So it's just a correlation, a Pearson correlation between the true association index and the calculated association index. Ideally, you want this correlation to be 1, to be a perfect job, but that's not often the case. So this will indicate the power of analysis. So how much your association indices are actually telling you about how much time these guys spend together in real life. And if you get a correlation close to 1, great job. Close to 0, go back to field.
So you're looking for a correlation coefficient that's closest to 1. So
Yes.
0.9, 0.8, that kind of thing.
Usually greater than 0.8 is already really, really good. 0.6 is good enough.
Okay, so, and then we'll just show you that your calculated association indices are as close as they can be to what they actually are in real life.
Yeah, the real, yes. And then the catch here is the more observations you have per individual, it's closer to the real thing you have. Let's see this. And here we estimate using bootstraps, and here the correlation use likelihood. Show me how. And then, so that's what we're looking for. So here's 2 cases. We have this is the true association index, the real association index, the actual proportion of the time they spend together, and this is the association index, the one we calculated with those indices, right? So if the social differentiation is low, you need the mean number of observations per pair that you need to have a reliable picture, R of 80%, so a correlation of 8, something like this. So that's a pretty good correlation. So if your society is very well differentiated, extreme, you need more or less, you don't need, the number of times you need less than 1. But that's ideal case. But if it's really low, you need like 500 observations per pair of individuals. You need a lot of data to pick up really what's going on. Usually what we have is a median differentiated society, And then you need more or less 50 observations per individual. That's still quite a lot to have a really good picture of correlation between the real life and the calculated index of about 80%. Now, a somewhat useful scenario, let's say 40%, then you would need at least 5 observations per individual. That's more or less where that threshold of observations per individual came from. So you have more or less a good idea of what's going on. So what you want is either studying a system that is pretty obvious what is going on and then you don't need much data, or if it's more or less homogeneous, you need a lot of data to get a good picture. So looking at the CV, actually at the S, social differentiation, and R, the social representation, it's very important. So we're just testing, okay, we have this pattern, we have these things, but how reliable all of these things is. And all boils down to the amount of data you have. And then for the permutation tests, we can calculate the power, the statistical power of analysis of these tests. So again, it depends on how differentiated the society is. Then we'll define how much data you need. The mean observed associations per individual for probable rejection of the new hypothesis. So if you're dealing with a very low differentiated society, or CV about 6%, you need a lot of observations to have enough statistical power to reject the hypothesis that they are associating at random. If it's super obvious, super clear, high, for example, you need not that much, 15%. And then one way, a rule of thumb to calculate this is this little formula here. So here is just showing the social differentiation, this one, and the mean association per individuals, which we call age. So if this value, the social differentiated squared times the number of associations per individual is greater than 5, you have enough power. So that's just a rule of thumb. And it comes from this simulation study here. It's just all, with this formula is all the data that we have above this line over here. So you need, for example, if it's super differentiated, not median, let's say, we have here, about more than 1 CV, and then you're gonna need more than this. You're gonna need
So, but this is a post-hoc analysis. So after you get your results, you say how good my result, how representative my result is. You apply this formula and you say this is, for example, this in case of the permutation test, or in case of so this you use this formula just to say whether your result, your p-values, etc., are good enough to infer anything.
Exactly. Or you can do beforehand. Before running the test, you go, okay, how much data per individual I have? I have about 140. Great. How differentiated my society is about this. Okay, let me calculate. It is greater than 5. Right, it is. So now I can test, and whatever the result I have, I know I have enough statistical power to test that. You can do either way. Or you can run the test and then, it's smaller than that. So maybe you're not actually rejecting the hypothesis. We don't have enough power to test. We need to collect more data.
But it's not a priori test before starting collecting data, because that, in order to detect something significant, how much data I need.
Yeah.
That's based on simulation anyway, so you could run your own simulations or use those simulations before you even go into the field.
Yeah, this is based on simulations.
So you can use a priori. This kind of,
You can,
take
yeah.
it.
So you can see, you need some data to calculate this. And
Exactly, that.
so, okay, my society is not very well differentiated. I know I need a lot of data per individual, how much more or less? Then you work out this formula here and then we get, oh, all right, I'll need 100 observations per individual, or something like that.
Yeah, I mean, you could look at published studies from your species or taxa to see if anyone's looked at the social differentiation before, and then simulate based on that, or you could just give yourself a range of values.
By social differentiation, what exactly do you mean? Is that how the individuals themselves like group in like as a part of their behavior, as a part of their I don't know, like species traits or whatever.
Yeah.
So I'm looking at
Yeah. It's it's also an estimate using Poisson likelihood math of the actual proportion of time they spend in real life. It's also a simulation, an estimation of the time they spend together, and we compare that with the proportion of time we calculated using the data you have in hand. Does that make sense? Yeah.
So the actual proportion of the time, is that the little numbers that we use to put in that triangle of the matrix?
No, that's
So that's that one, okay,
Yes.
so that one is like the one that we got with like 2a over 2a plus b plus c, that
Yes,
calculation over
this
there,
one,
so that
yeah.
one is there, so how do you get the other one?
Using
Oh,
likelihood methods, then you're gonna.
okay, so
There's a
that's-
pretty complicated way to.
okay.
So basically, if you were there to observe all the time,
Okay,
that
that would
is
be the
what.
actual, okay, so.
And the coefficients that they calculated that is your
Got
data.
it, okay. So the actual is still like somewhat of
Yeah.
estimates based on still on
Yeah.
statistics.
Yeah,
Yes.
it's
Yes.
confusing.
And you get it with the complicated method that we haven't gone.
Correct.
Okay, that's what I was
Yes.
confused with, how do you get the actual? Okay. So you're always hoping that there's someone else that has done that before?
No,
Well,
no,
it's-
that's where you have your distributions. You use your distribution to estimate your
The actual?
Yeah,
the real.
the
the
true
true.
CVs are calculated from your data based on one of those two methods.
Oh, okay, which I don't know what that's like.
Yeah.
So that
My life.
in your data you see an individual 4 times with another individual. How much that is the real situation, or maybe because you have some observer bias that
Okay.
you haven't seen them all the time.
All the time,
It took me a long time to figure out this thing, why,
okay.
how I
So the way
calculated true.
you calculate, the way you calculate is using likelihood methods, and it explained in this paper here in the appendix.
Okay.
It's one of those like, if you really want to know.
Well, but then, okay, what if I don't care about the formula, can I ask R to do it for me?
Yes.
Okay, that's what I was wondering. Okay,
Or saying Socrates is.
or SOPROG, okay, so there is a way to ask the programs to do that for you?
Yes.
Okay.
I'll
This
show
is
you-
those things again, you know, you don't
You
ask
don't
and
ask.
accept.
Well, but what if I have to do it and I need to know how to do it?
I'll show you right now how to do it then.
Okay,
When you're, let me see.
sorry, I guess everybody knows how it's.
No.
Anyone that
No,
doesn't?
no, 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 no.
Okay.
So when you, let me see, when you put your data here in basic
Wait,
data,
let me resync it. I think that's, no, that's exactly the same, okay?
so when you put, yeah, this is remote, but,
Strange.
so the social differentiation, when you put in the basic data, you're gonna find, it's impossible to read there, but over here you have just an option. You click there and see, yeah, give me the social differentiation, and then it will
Oh.
calculate for you.
So from the data that I input, so from my data set, I just
Yes,
stick it in there and then I ask him
yes,
and then based on the number that comes out, then I know how many observations I need.
yes. So here in basic data, if there's anybody following this part, in basic data here, you click over here and it will be, the last option will be social differentiation.
Yeah.
It also gives you the option to run standard errors by Bootstrap. You can do that, but it will take a little while. I won't do it right now.
What if we do the social differentiation then on the output? Which one is the
It will
number
give
that
you
it
over
will-
here. So in the output, let me see if I can make this bigger. So the output it gives you, so here's the mean associations per individual
Mhm.
and per group and per individual. So in this data set is 56, not bad. And then it gives you estimate of social differentiation, which is the CV of the true association index using Poisson approximation or using the likelihood method. So we run that crazy method for you, and this is your S.
Okay, so for the S that is higher than 0.5, is that what it was?
No, it's
No.
S squared times.
So this is 0.8 is indicates pretty
Good.
good, well differentiated. This is the
Yeah.
differentiation. Right? Here.
Yeah, you.
Okay, so 0.5.
So it's a well
Okay.
differentiated
So
society.
because of that, then we need less observations.
Yes,
Okay,
because the
then-
pattern is
okay.
already more or
All right,
less.
that makes sense.
Now let's see
That
the
was missing.
let's see the age. So the mean observed associations per individual. It also gives you over here the mean association per individual here. So age is 56.6. And it also gives you the R. So the R using Poisson or likelihood is usually better. So 0.897. So we have a correlation of 90%. So that's a good representation.
So S and R are the same number?
It just happens.
Oh, it just happens, okay, not necessarily, okay.
So if you use Poisson, just it would be less
Yeah,
complicated.
you got it, okay.
Yeah, so we have a good representation. So 80% of the real life is correlated to our association index, so that's good. We have a lot of data. We have 65 observations per individual, and we have a society that is very well differentiated. So if you do that, so to calculate the power for this, the permutation test would be this. And if it's greater than 5, we have enough power. And I'm sure that would be.
Doesn't this be, can't you ask Al to add that
Yeah.
formula already?
So, wait,
Yeah.
so that S of 0.897, that would go, that would, that would,
That'll be the CVT.
that would be the CVTA.
This one, yes.
Yes.
Okay.
Yes.
Okay, so if, because you have, so then that falls into the high social differentiation.
Yes.
Okay, so then you only need less, okay, that's
So you
Yes.
need like only 5 observations instead of 500.
So,
So if you want to see if you have enough statistical power, we can just do that. 0.8.
Just like how you do the actual.
Oh, yeah.
So you do it over there.
Oh, you never heard.
56.
Yeah. So yeah, it's greater than 5. We're good to go. Now we can run the test, and whatever you get from the test, it means something. Good.
So, but this one is after you have your data.
Yes. So ideally you collect your data and then you come here and can run this part and see, okay, we have enough power, let's
Okay,
go
so
ahead.
basically, what, like, in a real life, just like in a real scenario, I collect the data for 6 months and I wanna know, am I done or do I need more? So I do this, if I have
Yes.
all this that fits, then I'm just like, I can go home, if not, I have to go back in the field
Yeah.
and keep going. Okay.
Correct.
So it's not really an a priori, it's just kinda like a halfway kind of thing.
Like Ryan was saying, you can run simulation to see how
Yeah.
much data you need
Yes.
to.
Oh,
come up
okay, but that's a whole other topic,
Yeah,
okay.
but it gives you,
I don't know, it would be fairly easy, you can
Yeah.
plug in some values and try, or even in the book, well, like your slide there is already giving you an idea of how much.
Yeah.
Yeah.
the editor here. Okay. Here it gives, oops. Yeah,
Can you tell
this
me
graph
how
will
much
give
that
you,
was my project? Just
Think about it
yeah.
now, rather than
so this graph will give you more or less, this is all simulation as well, but here's the social differentiation and the mean associations per individual you have. So if you have lower social differentiation, you need much more.
Yeah.
So you need to be up.
Yeah, but if you don't know what the social association
Yeah.
is, then
So you need to calculate something.
But
Or
what
you
I
can-
meant was you would expect something like a killer whale to be very socially differentiated, of
Yes.
course, but something like a shark or a bottlenose dolphin to have less social differentiation.
So you can use other studies to kind of predict
oh,
more.
so
or
that's
less.
what I'm saying. You're hoping that there's someone else that has done that before.
Yes.
Yeah,
Already.
At the, it's not too unlikely that situation nowadays
that's
quite a good background information, quite a different species.
Thanks.
Yeah, so there in this slide there's like the output and some annotations, so just so you know
Oh, okay.
where things are. But I was how to make a
Already, yeah, they calculate that thing
just
already.
put everything.
Mauricio, you should have a thumbs up or a thumbs down.
No. Sweet. Good. So that actually is still the first lecture. So welcome to the second one, which we're an hour and a half late. But so in this second part, we can go quicker through this. I'm sure you guys have seen this before. So the idea here is, so we had our matrix and we test, all right, they're not associated randomly. There's some structure over there. So I'm gonna present some techniques to look at this matrix in a more visual way, to see if, where this structure is, if there's some groups over here, if there's, yeah, I'm just gonna look this in a 2D space now. So the two techniques we're gonna look right now is principal coordinate analysis and no-metric multi-dimensional scaling. So PCO and MDS, and MDS. You guys are you guys familiar with this? Have you done? No? Anyone? Yes? No? Okay. So now just want to represent that same thing, that matrix. There's many ways we can represent that. Just plotting the histogram like we did yesterday, or as a network, or as a PCO, which is similar to MDS and clustering. We're gonna look now at these two guys over here, and they come from multivariate statistics. So there's some similarities. The idea here is the same, it's just different techniques to look at this. We can, for example, a network or a sociogram is simple, we have no assumptions at all, but it can be very massive if you have a lot of data. It should be PCO here. Change that. Now PCA. We can check if it's a good representation. Essentially, we're just seeing the closer the individuals are, less distant they are, so more similar they are. So if you start looking at groups here in this space, that means these guys tend to be preferred association. You can have these guys that interact with more or less everyone, but not very strongly. So it's just a different way of looking to our matrix. Or you can plot into a hierarchical clustering like this, when hopefully you're gonna see clear groups. So you're looking for the large, here are techniques for looking for large scale structure in your data. So we're not much concerned about the pairs now, but if looking from afar, if we can get large scale structure. We're gonna look at this during the afternoon, and right now we're gonna take a look at this type of relationship and presentation. So here they are all exploratory analysis. Which variables? So here our groups are our variables, and our individuals are our samples. It's a little bit different than yesterday. And what we want to do here with this multivariate statistics techniques is actually explore our data, explore the large pattern of it using ordination. So we're going to put our samples, which are our individuals, in order. And we can do that using a PCA, which you're going to see in 2 days from now, or a PCO, which is a principal coordinate analysis. So we're looking for groups in our data, or multi-dimensional scaling using MDS or MDS, or later on a hierarchical analysis. So to ordinate all of these techniques there, we're trying to ordinate our data, put them into order. So arrange our samples, remember our samples here are individuals, along axis. So if you have just one variable, that's easy to do. So if you want to organize ourselves here in the class, we have 5 individuals, you want to organize them according to height, for example. You put in one dimension, you can put them along this line, for example. The shorter one to the higher one. Easy enough, right? Now if you have 2 variables, so yeah, we're just ordering our samples, individuals now, according to variables. In our case it's group, but in this case if it's height, we have just one dimension from the lowest to the highest. Easy enough. Now if you have two dimensions, 2 variables. So we have, say, weight and height. So we're gonna organize them in 2D plot, super easy. Fair enough. But now we have a different, they are in a different dimension. We have the original variable here. And then we're gonna extract other axes, the U-axis. Then we'll try to summarize both variables, both criteria. So the axis, the way you do is, you start with one. You try to draw another axis along when you capture the higher variability of your data. So in this case, it's this way. Can you see our data is dispersed like this? So if you draw a line over here, we get most of them organized in this way. Can you see that? And then the next one would be another axis that is orthogonal to this. So you need a 90 angle degree with this one. So in this case, we have here. So all of our data now are in 2D in this space. So we have our original variables here. We have 2 other ones, and they are orthogonal with 90 degrees according to each other. And they explain one of them explained the most variability of the data, the most dispersion, and the other one comes in 90 degrees. So this is easy in 2D. Now, so this one will always explain the majority of the variance of the data. Now, if you have 3 variables, it's still pretty easy. So we have weight here, height over there, and say age. So in 3D, we have that one that gives us the higher variability. We have the second one that is orthogonal to this. And a third one would be also 90 degrees to this tube, but then imagine sticking out of over here. So we have kind of a sausage now. And this, yeah, that's a terrible ellipsoid. So all of our data is in this 3D space over here. That's still easy, you can still see. But now what happens when you have multiple variables, so more than 3. You can do in 4D dimensional, 60 dimension, or n dimensions. So it's just hard to visualize. But the idea is the same. Every time you add one dimension, one variable, you add another orthogonal axis through it. So if, in our case, each group is a variable, then how we can represent that in n axis? So it sounds impossible to the eye, but so normally our variables are not orthogonal in the way, for example, the groups of individuals. So we have to transform your data in somehow that we can represent, say, 100 groups in 2 or maybe 3 dimensions. And that's the goal of TCO or MDS with other multivariate statistics. So the goal here is to reduce the number of dimensions. We're going to have this large body of data, and we're going to bring it into a manageable set of data. So if you have here, first, symmetric dissimilarity matrix, individuals, or whatever you want. We transform that into a distance matrix. So we're going to see how distance B is from A, and C is from B, and so on. And then we plot that. But just remember that the association matrix in our case is actually a similarity. We have to transform the similarity into distance. So if our association index varies from 0, which is very different, varies from 0 to 1, when you transform that into a distance, the ones would be very different and the 0 would be very similar. It's just that way. So in the PCO, what we try to do is plot all of those distances. So for example, if you plot A and B, they are separated by 5. A and B separated by 5. Then you add C over here, which is separated by 3 from A, right? And by 7 from B. Mm-hmm. Good. And then I keep doing that. And so the idea here is you try to put that in 2D following the original data. So we represent 4 points and 2 points in 1 dimension, 3 and 2, 4 and 2. So essentially k points in k minus 1 dimension. But this is not always that easy. Sometimes you don't have you have the triangle inequality. So depending on the data, you start with a pair, but then when you add another one, there's no measure they're going to fit exactly the way the data is. So you cannot represent that. So that's how we use principal coordinate analysis. So here's how we do. So first you take a distance or dissimilarity matrix with k units, k individuals, represent as k points in k minus 1 dimensions, and if the triangle inequality holds throughout, and then we find the direction with the greatest variability, and that's going to be our principal coordinate. And you do that, the second one, for this, the way I was presenting with the 3 data. You try to find, first you find one axis that represents the greatest variability of the data, and add another one that is 90 degrees to it, and another one that is 90 degrees to that, and those are your new axis, your new, what we're gonna call PCs, in this case, principal coordinate. And then at the end, we're gonna take this, just the first 2, or maybe the first 3, and replot our data with these 2. These guys will summarize most of the variability of the data. So we take, if you have 25 groups, so 25 dimensions, you're going to take the first two, then use just the first two as a summary for the 25 of them. So this reduces the number of dimensions of your data.
So instead of plotting the sample, you plot the variability of the sample.
You plot the sample again, but instead, if you come back here, instead of plotting height, weight, and age, I'm going to plot this using this thing. Now I have U1 and U2. So I'll replot the data using these guys now.
Yeah.
So if I have 25, I'll have 25, we're talking about axis here, but I'm just going to use 2, maybe 3, maximum 3. So the idea is replot your data in 2D. So summarize, and that's why we get usually the first two, because remember the first one contains most of the variability of the data. The second one will contain this part, and that's a good representation. Sometimes, okay. Is that clear for everyone?
So can you go one before?
Sure.
There was one thing. If the triangle inequality all throughout,
Yes.
should be the triangle equality all throughout? So basically, if you can plot, you
Yes.
can goes to the PCO.
Let me see. Good question. I don't remember that part. Let me see. No, that's when you can plot. Then that's why. I think that's why you cannot rely on these guys. Then.
So if you can't plot it,
Yes.
you go on the PCO.
Yes.
Okay.
But very likely you won't be able to plot 25.
Or you don't want to.
Or you don't want to. Yes.
Yeah. Okay.
So in other words, what it means, the principal coordinates is actually the eigenvectors of your distance matrix. Sure. And the eigenvalues of your distance matrix give the proportion of variance these guys account for. Just throwing out there. So, okay, now in the social context, that's easy for height and weight. But then in social context, we're dealing with a symmetric similarity matrix, so not a distance matrix. And we want to just transform that into a distance. So here in the plot, when we have our new PCO, so PC1, PC2, and we have individuals here. So A and B and C, that's two idealists. So this is the distance. The shorter the distance, the more similar they are, right? And the greater the distance, more or less similar they are, so more distant they are. Anyway, so if you have the association matrix here, so A, B, so A and B will be, say, 0.8 association index, so similarity. That means when we transform to distance, so we do, say, the square root of 1 minus this will be a smaller value, and this guy will be larger value. Okay, so it's just the opposite.
The square root is just to account for sine?
That becomes the Euclidean distance.
Yes.
Right.
That's right. Which is the distance and the Cartesian plot.
Yeah, because it's being okay, yeah.
So here's an example. Good. Here's an example. So we have for the GKD scene in a feeder. So for all the bird people over there, now everything makes sense, right? There's a picture here. Great. What else do we need? So here's the proportion of time they spend. So this guy, why didn't you give a better name for them? Cow and AO free. They're seen together 18% of the time. So when you transform that to distance, the Euclidean distance would be 91%. And let me get a small one here. This 0.02 will become 0.99. Let me get this big one. Wait, so. And
It's getting less and less, yes.
okay. So a small proportion of time turns into a huge distance, and a greater proportion of time turns into a not so huge distance. So SOR and is here. Yeah, so this guy, BJO and SOR, anyway, these two guys here, they're not so far apart as they are for, where's it here? So, anyway, he got nothing. If they call Joseph, that would be super easy. Anyway, another important output of this is how reliable this is. So notice that we are plotting this not into 1, 2, 3, 4, 5, 6, 7, or whatever dimensions they have, numbers of group. We're just plotting in 2. So here's the first PC, the first principal coordinate, and here's the second one. How much variability do we have in this one, in this dimension here? So we are ordering these guys along this axis, this axis. So along this one here, we have 22% of the variability. It's not that much. And then when you add another one, you have more 20. So combined, you have actually 42% of the whole variability here. It's not the best plot in the world. And
that's why you might need a third.
A third one. If you add a third one, it goes up to almost 60%. So it's good. Usually, rule of thumb would be more than 75%. So this is not the best representation you can have for your data. But yeah, with this kind of association data, that's more or less what we get. So PCO is one option, but not the best in the world. I'll just show you quickly how to do it in sock problem, which is super simple. You require just a click of the button, actually. So once you're in this,
Wait, let me see whether this is alive. Can you make the character large? When you change to these other windows of yours, it's make the character smaller, and so you need to change. Yeah, most likely. Yeah.
so here in that association window, you have this option here. So once you have your matrix in and all defined, you just go ahead and click this guy. And you ask we just ask the font size, right? That's good. That's good. 20. And color is no, whatever you want. And there you are. So we will just plot for you. So we plot for you here, and so we had 20 individuals, and here the percentage explain it. So with two PCs, we have 78% of the variability accounted for. So this is a good representation. So you could use that. So you can see, for example, there's some groups, some pairs here that are always seen together, that kind of thing. So, yep.
Sorry, you want to carry on?
No, that's it. And
How it goes up more than the cumulative more than 100%?
It does.
With 3, the cumulative it goes to 104.
Oh, yeah. Great, I have no idea. I've never looked into that. Good question. I don't know what's going on here. And then it goes back to 100.
Yeah.
Yes, something's wrong here.
Because it starts to kick in the negative values,
Yeah.
then it goes down to 100. Because there's 20 individuals, you said.
Yeah.
So obviously, if you're able to represent in 20 dimensions, you will get 100%.
Uh-huh.
That's fine.
Yes.
How can you have a 100?
No, it's big. This is anything in R, so this is your.
Yeah.
So when you run that,
The outcome chart.
uh,
This is just
when you run that in R, it gives you an error message for these kind of things,
Is it? Okay.
saying that you have negative eigenvalues in it, which is the case here.
There, yeah.
So, yeah,
Okay, but that's this.
it should, yeah.
As long as you reach 70%, then the 75%, then you use that.
Yeah, that would be the idea. But that's a good point. I never looked at you there. Let's see. So, what else do I have here? Let me try it run with a different data set. Yeah, same here.
Okay.
Anyway.
So here you use 3.
Yeah, here use 3. So if this is not a good representation for my case, I can add another PC or try another technique. For
Okay.
example, the MGS.
Okay.
You can do, there's a script for running this in R. I don't know if you guys want to do this or should I move on? There's,
No, don't worry. It's just my curiosity.
I'll just, I'll move on to MGS and then we do both in our view as well. Because in Sakura it's just clicking on it. But it's good to see how to do step by step in R. Okay. So this is how the PCO works, principal coordinate analysis. And which is similar to what we call metric MDS, multi-dimensional scaling. And we have what we call no-metric MDS or non-parametric PCO. They're pretty much the same. The difference with these guys is an iterative process, and the major difference is we have to define a priori how many dimensions we have instead of calculating all of the PCs and say, oh, do I need 3, 4, 5? In this case, I want to do in 2. So we start with 2, and then he tries with interactions to get you the best picture you can get in 2 dimensions. So that's the major difference actually. So you have an association matrix here, same idea. So given an association matrix between units, so in our case individuals, it tries to find a representation given the number of dimensions you want beforehand, and trying to preserve the pattern you have here. So we're gonna try to plot this in 2 dimensions, for example, and then there is a stress metric to show you how much your representation is related to the real matrix. So the way it works, more or less like this. You start with a similarity or usually dissimilarity matrix, give the number of dimensions, usually 2, and then it plots more or less like it plots for the PCO, pretty much same idea. And then he orders this distance on the plot and comparing the distance that you get in that plot with your original matrix to compute what we call stress, how different these 2 things are. And then it tries to juggle this point in the plot, and then to reduce the stress, and then keeps doing this until you reach the best solution, or until the stress is stable. And when it reaches to that point, it gives you the plot, gives you the stress, and then you decide if it's not good enough, you can try it again, starting with the different initial parameters. So same thing. You give the matrix, give it a number of dimensions, it plots initially, orders, compare with the original matrix using the stress, and keep doing this until you get the best option. So it's an iterative process. So what is stress? That's what it is. It's the distance that you get in the plot. So this is your real association. So you're gonna have a matrix here with some values over there, and you're gonna have a plot here. And you're gonna have one value in the plot here. So it's just the difference between the original value and the one in the plot divided by this difference squared, and and then you make the it's just a standardized distance. So one is predicted using the distance on the plot, and the other one is the real one. So ideally you want this to be as low as possible. Stress, and the less you can get, the better for you. And that means when it's up to, I think, 7% or 10% is good enough. It's a good representation. If you have a stress too high, that means the distance you're seeing in the plot is too different than the ones you're seeing in your original data. So not a good representation. So actually what he wants is how well, because you have this in nature, and then you go there, collect a bunch of this, and come up with this thing. And then you're not satisfied. You want something more visual. Then you want to plot like that. So the question here is how well this thing represents this, and how well this thing represents this thing. So that's why we calculate this stress. So it's an iterative process, so there's no unique solution, depends on how you started. And you might want to start with, try different starting positions. Oh, now I remember why this guy's here. I was just like, what the hell? And so there's different, possible different definitions of stress. That one is the common one. And, all right, so how many dimensions? You choose beforehand, usually 2 or 3. You want to choose the ones that reduce the stress. So a stress less than 10% will give you a good representation. Another way you can do is you can plot the script plot. We just show you the percentage of variance explained by each dimension. So when you have these, what we call this elbow here, so you can see adding another one won't improve that much. So with Q, you have already a lot of variance explained. If you add another dimension, you're just going to add a little bit more, so not that important. So if you want to do this more, with more methods, you choose how many dimensions you want. You can run and take a look on this elbow pattern here. So how do we choose between metric or non-metric? This is nearly similar to PCO, actually, pretty much the same thing. So this is pretty much the same as PCO, unless, and that might be that problem, if you have too many negative eigenvalues, like we did for those two examples. So maybe.
So when you have these negative values, you use the MDS.
That would be the case, yeah.
Okay.
No metric does better with fewer dimensions. So usually MGS is preferred over PCO. So here's the difference. So one is metric, the other is no metric. This one requires a distance matrix. That's why we have to calculate the Euclidean distance between the associations, which was 1 minus the association index in the square root of it. That's the. In MGS, you can run an association matrix. In R, you have to run a dissimilarity matrix, just to make it more confusing. Just because the way the function was written. One is there's a unique solution, the other one is iterative. You try and try. This is better if you have a lot of individuals, and this is better if you have more or less up to 100. You can usually use more dimensions here, less here. In one you design after, looking at the proportion they explain, and the other one beforehand. And that's it. Let me show you an example.
Sorry, that one is MDS or MDS only?
And this is MDS. It's no metric. The metric MDS is pretty much the same as the PCO. Yeah. So it's more confusing. So I'll give you a quick example with sperm whales. So this is the genetic distances between sperm whale groups. So which one here is a group, and how dissimilar they are in terms of mitochondrial DNA. So this is one. Good. So we have three ways of representing the metric MDS or PCO. So we have two dimensions here. This is how it displayed. Same thing using the MDS. So we got a lower stress here. And then this is this guy with 3 dimensions, even lower. So in this case, the best representation will be this one. Although, it's not as visually attractive as it is, but technically you want a representation that gives you the lowest stress possible. Remember that the stress is the overall difference between the distances you're seeing here in the plot and the ones you're seeing in your matrix. This is truly just a different way of looking at that ugly matrix. So you look at those 2 billion numbers and what's going over there. This is a way of seeing, but you're gonna lose some definition. You want to lose the least definition possible. So for this situation, this would be your way to go, or maybe even this one. And, okay, now I can show you how to do in our subprog if you're not hungry enough. Shall we go over? For those that want to run away, feel free. It's just, that's just it. Really quick. Should we do it? No answer. Good. So in subprog, it's very simple. Just gonna click here and MGS. Let me see if I can increase that.
of your MDS is greater than 10, then you should probably discard it and try again with more dimensions, or is there like a window like 18, 10, and 15 where that's sort of okay, but
Well,
it's kind of pushing it.
Well, this is all subjective, right? Even the 10% is arbitrary. It's just a guideline. If it's close to that, you can, if you provide that information, here's my plot and the stress is 15%. So you decide if it's good enough. Then if you try, you can try with 3 dimensions to reduce, but sometimes I find it way too hard to visualize anything in 3D. So I would prefer personally for a little bit more stress in 2D, but then you show this is what it is. It's like 15% off of the original one. But you can see this and that. Those are all exploratory analysis. You have no idea what's going on, and you want to plot and see, okay, is there any pattern here? Yeah, it looks like we have these 2 groups, looks like we have these 2 pairs here. It's more, you're just exploring the whole thing. You're not testing anything yet. So, yeah. And then, depending on the type of pattern you see, for example, if you run MDS for this guy, then if you see, okay, it looks like we have these 2 big groups here. I wonder if those are real groups. Then there's other ways of testing, which we're going to see tomorrow with modularity, or even this afternoon with clustering analysis. So it's a visual way of exploring your data. So if you want to run the MDS, you just click on multidimensional scaling here, and you give us a bunch of options. Most important is the font size. So you have to decide beforehand how many dimensions you want. Let's start with 2. And here we go. We can have the no metric. There's a bunch of ways of calculating stress. The default is that one I showed you, so no metric stress. And here we have 2 different starting points. Remember, depending on the starting point, you can have a slightly different solution. So we might want to run this a couple times. So let's start random and make it. So, some errors over there. So the output would be the plot and your stress. In my case here is, well, I think I'm using a different data set as you guys. This case is 18%, not the best of human life. But let's try running with 3. So now in 3 dimensions we have a stress of 12%, but notice that the plot has just 2 dimensions, but it was run in 3 dimensions. Any questions on this thing? Super easy? Nope. I'm hearing a lot of error messages there. Let's see. You choose this. So if you want to run the same thing in R, you can do this. Okay, so should we run in R? Do you want to, any errors there? Do you need help?
Rob, can you try keeping your package again? The mute again? Yeah, it just doesn't read it well. I did exactly the same thing that they did
Forgot to put my
than it did for the other
But no.
one.
Yeah, because I had to readjust
Well,
That's where I don't.
I changed the arrow to desktop. And it reads it.
Well, so, yes.
And then I changed the packaging.
You don't remember what data sets
local
that
source
previous
and
company.
which is what I did exactly
Is
for
there
weekend,
a pro?
and then just the regular.
Yeah. Yeah.
It doesn't tell me to install, I even tried to like stick it in the
Yeah.
phone, it still doesn't.
Yes.
But I
The 2.6, I think you
Or
can
it's
still
when
do
you
it.
start changing, like when you change it, like that becomes available.
If you can do it there.
And then
Great.
But you don't know.
I don't actually. That's why I never use my these devices to TV. Usually we do it. Yeah, this year, it's started. It's just all good there? Good. So let's do an R thing. All right. So are we good to go or?
do we need this package?
Do you need vegan for it?
I think so. Maybe not. Not for the entire thing. So our first example would be the genetic distance between spermatocyte groups. So here's the data.
So, sorry, I was absent.
Yes.
So here we, instead of looking the percentage time they're close as a variable, we look at the genetic distance as a variable.
Yes.
So basically we can run those matrices on anything, any variable
Yes.
that relates to more than one individual. Is that the
Yeah.
concept? Okay, cool.
You could do this in GS or PCO on, say, home range overlap. Or,
Yeah,
Yeah,
right.
or anything.
Okay.
So
I
any
didn't put it in
any
here, I have vegan.
index between them. Yeah.
Individuals, okay.
This is also super used in if you're working with community ecology, for example, when you have a bunch of species in different plots, for example, or different. If you're doing, say, underwater transects and looking at how many fish species you have there, and you want to compare transects, or you want to compare abundance of a given species in different places. So it would be always the same, it's the same basis. Or, yeah, it's pretty common people that work with like plant biology, they go in the field with a plot and count how many species they use. And then you do that in a site and then compare like regin. It would be the same. Seem like the structure of ecological communities that kind of thing.
Because it was looking before, no? But then it
Good.
and he was sorry that I need to have it for you.
So whenever you're ready, we can. Oh, good. So the first example, we're going to run a PCO on the genetic distance between spermatocyte groups. So we read the data here, and first thing we have to do is just transform into our distance matrix, which is essentially just the lower part of the matrix, excluding the diagonal. So with this function, in CMG scale for the stats package, it calculates for you the two PCs over there. And there you go, we just plot them. It's super easy. So first, here and there you go. 2 lines of code. You can specify here the number of dimensions you want. For example, you can run 4 and see how many you have. Here's the eigenvalues. And one way of looking if the PCO did a good job is also looking at the goodness of fit metric. We'll give you 2. The more dimensions you add, the higher would be the goodness of fit. So the more dimensions you have, more likely your data will fit with the representation. But you don't want to plot, for example, 13 dimensions. So if you can do it in 2, it would be good. Let me just see if I can do that. Yeah, in 2 is just 46%. It's not that great. Here's a little explanation of how you interpret the goodness of fit, if you're interested. Because we are a little late, I'll leave that for you. The second example is using an association matrix. So this is for the totality data for the Guiana dolphins. And it's just an association matrix like all the others we've been working with. So remember, to run this, we need a dissimilarity matrix, so we gotta subtract 1 out of those values. Is that alright? Is that clear for everyone? Good. We'll do this.
The subprog instead does it automatically.
I think subprog runs on the similarity, and this function in R, it needs a dissimilarity, so it's just the way the guide program. So here's our dissimilarity matrix. So for example, A1 and A4, they were associated 14% of the time, so now they are distant by 86% of the time, just the opposite. And we're going to run on 2 dimensions, which represents pretty bad, 30%. But let's see how it does. It looks like this. There's not much clear structure over there. You can see maybe these guys here. There's some preferences around, but there's lots of. It's pretty fluid. Some guys tend to interact with everyone, or pretty much no one. So it's not that very clear of a pattern. We could, let's just suppose that individual 1 to 10 and 20 to 80 are adults and the other are young. Just to see this visually, you can create a vector here. Just any vector saying these guys are adults, these are young, these are adults. And then just to change the colors and the plot, see if there is any visual correlation between age and association. So what I'm doing here is just replotting with different colors, not more than that. And it doesn't look like as you expect. I wouldn't expect that the young guys will hang out by themselves anyway.
They're all pretty big.
Yeah.
Sorry?
You get a lot
Yeah.
of parents with offspring.
Yes, that would.
Several cases.
Yeah, that would explain. So we don't have like a community of young rebels. It's just hanging out with their daddies. So to run the MDS, here's the code as well.
Sorry, how do you know that those are parents?
No, it just it's
You specified it beforehand.
Yeah.
Yeah, you specify beforehand which ones are adults and which ones are parents.
Yeah.
And then you color the data set according to that.
Yeah, that's
Yeah.
because of
We don't-
age.
We don't know that they are parent offspring pairs, but you would.
Expect. Okay, it's not that. Okay, no, I thought I wasn't reading something that you guys were seeing. Okay, cool.
Yeah, it was just like a hypothetical case.
Let's say.
Yeah, let's say these are, I don't know, females and males, and then you can color them in different ways, see if they.
Yeah, no.
Okay, so for the MDS, gonna do the non-metric one. So let's read this data. It's the fake data on birds. So sorry, bird people. That's probably not true. What's happening here? So this might be necessary. So we need again to transform into a dissimilarity matrix. So we're gonna do 1 minus these values. But because we have a lot of zeros there, the only thing I'm doing before is just adding a tiny value, like 0.00001, just so when we subtract 1 out of this, it won't be a negative value. Does that make sense? It's just like a trick. So this is the original data. We have lots of zeros here, zero similarity. So when I do the dissimilarity with 1 minus this, so 1 minus 0 might give you a problem. And so I just add like 0.00001 just to be close enough to 1 but not 1. Good. Alright. Make that into a distance matrix like this. And now run the MDS. So to run the MDS, we're going to use this function called meta MDS. Which is in package B. You might need that. So C is a iterative process, so it runs once and calculates the stress. Remember how different the plot is with the matrix? And then okay, it's too big, and it tries to run again and calculates the stress, reduce, this is the new best solution, let's try again, and you keep doing it until it reaches the best solution. So the best solution is the one with which the stress is 0.075 and so on. And we just keep trying a bunch of times. And that's it. Then we plot it. And look how different it is. Oh, that's a different data set. Never mind. So this is a different data set, a fake one, where you can see perfect patterns, right? That's so, I wish it was like that in the real world. So we have, this is what MGS is good for. If there's any pattern, you can see, okay, so these guys are clearly best friends, and these guys are. And these guys, they stink, I know. You know, I have any friends at all. So let's see the stress of this. Yes?
Can I, yeah, maybe I should not have this question. Okay. In this function that we use to calculate the MGS, there is an argument called DWA scores.
Called what?
DWA scores.
Yes.
If you look at the function in itself.
Let me see.
And this argument says calculate species scores using function WA scores. And I was just wondering if this is something you want to use if you are like on a weighted network.
Let's see.
Yeah.
Good question. I honestly don't remember why I put that in.
That's why I said maybe I should not have this question.
Average score of species.
Yeah. But maybe it allows you to like add a weight, so then you may have a little bit more weight, and then somewhat the matrix uses this I'm sorry, it's not, I'll
No, I
do it. If you don't know the answer, I'll look into it.
I did, yeah, I don't know, but I should because I put that in.
I'm not expecting, no, you
It's
should
fine,
not.
you're not using it. So
Yeah.
It's false.
Don't worry.
I'll look it up. Another thing.
No, it's
So we can see the stress is calculated in this in the object here. It gives stress somewhere here. So you can take that out using this. So the stress is 7%, so not bad for fake data side. We could do, remember that MDS, the one thing you have to specify the dimensions beforehand. So if you want to do with 3 dimensions to see how it looks like. Now we look at the stress is much lower because the more dimensions you put, more close you get to the original matrix. But then when you plot that, it doesn't look good. I usually don't see what's going on. For example, here, it looks like here you have lots of the dots on top of each other, so it's really hard to see what's going on anyway. So we have this group of individuals here, group of individuals, and those 3 solitary ones. I don't find that very useful as opposed to this, which is stress is a little bit higher, but it's much easier to read what's going on, right? So it's another choice. That's it.
So you, basically what you're saying is usually it's better in 2 dimension
I think, yeah, it's,
from a paper perspective.
I think so. Unless the stress is way too high, and I don't know. I'm not personally. I'm not a huge fan of 3D plots, but not that I come across way too many 3D plots in my life to have as a label for myself. But I think it's easier to see like this. In this case, it's simple enough. So if you have more information on the individual, say, you know the sex of them, you could try to overlap this information here and see if the groups are defined by sex or not. So again, PCO and MTS, they are this exploratory analysis. So it's just the association matrix, but instead of looking at this or looking to something like this, looking to this and looking to this is way more easier to see what's going on. But it's not, it's just plotting this into this. So PCO and MGS, they're good for that. Start exploring. With this data set, say, okay, so there's 2 groups here. Now, along the workshop, you're going to see ways of testing. Are they really groups? What is defining this group? Is that sex? I don't know, is that age or genetic relatedness or whatever it is? So there's other techniques. So from here, you start getting this new hypothesis. Since you know, okay, there is structure here. There are preferred associations and avoided ones. They're not associating at random. So let's see if there are more than one group. What defines that, and so on. So that's one level of structure we can see in our data. And that concludes our first part, finally. So thank you, everyone.